Now we shall discuss about electrodynamometer type instrument. Electrodynamometer type instrument. Or electrodynamic instrument. Electrodynamic type instrument. Or electromagnetic moving coil instrument. This instrument can be used for the measurement of AC quantities like voltage, current, power. Voltage in the AC circuit, current in the AC circuit, power in the AC circuit. Okay, this instrument can be used for the measurement of voltage, current, power in AC circuits. That is, this instrument can be used as voltmeter to measure AC voltage. This instrument can be used as ammeter to measure current in the AC circuit. This instrument can be used as wattmeter to measure power in the AC circuit. Mainly, we prefer this instrument as wattmeter. So, mainly this instrument can be used. This instrument will be used for the measurement of power. Okay. Mainly this type of instrument can be used as wattmeter. This is used for the measurement of power. Mainly this instrument is used for the measurement of power, right? Okay. Now, coming to the difference between PMMC instrument and electrodynamometer type instrument. Okay. Coming to PMMC instrument. Here, electrodynamometer type instrument. Type instrument. Now, coming to PMMC instrument, in this instrument you are going to have curved pole faces like this. Okay, this is what permanent magnet, right? Okay, this is permanent magnet. Okay, north pole and south pole. In the presence of magnetic field, we place moving coil. We place moving coil inside of this magnetic field. Okay, this is top view of moving coil. Okay. So we place moving coil, right? Okay, anyhow, this moving coil is connected to the spindle, and the spindle carries pointer. If it is moving means spindle will be moving. If the spindle is moving means pointer gives deflection. Pointer moves from a zero deflection, right? Okay. So instead of this magnetic field, we place moving coil. Okay, this instrument works based on motoring principle, right? Okay, coming to electrodynamometer type instrument, this also works on same principle, that is motoring principle. Coming to the construction details, instead of using permanent magnet, here we use electromagnet. Let I is the current which is flowing to this. Let me pass same amount of current to this coil also. These two coils are fixed coils. These two coils cannot move. Okay. Now when you pass current to this coil as well as this coil, then flux will be produced. Okay. Now let me place moving coil inside this magnetic field. Inside this magnetic field. Okay, then if this is the direction of current, let me join these two coils. Then both coils will carry same amount of current, right? Okay, so this will be the flux. Anyhow, you're going to have more number of flux lines. Okay, this flux will be linking this moving coil. Okay, the only difference between these two instruments is here we use permanent magnet, here we use electromagnet. Okay, here this is what, this is electromagnet, here we use electromagnet. Okay, here we use permanent magnet, that's it. Okay, here TD is BINA. Here TD is directly proportional to current. What is the current? What is this current? This is the current which is flowing to this moving coil. Okay, let I is the current which is flowing to this moving coil. Okay, now here this moving coil also carries current here. This also carries current. Okay, so these two coils are fixed coils. So let IF is the current which is flowing through these two fixed coils. Okay, let IM is the moving coil current. Okay, this is what, this is IF, this is also IF, this is IM. Okay, now in this case only the defect narc is depending upon the current flowing through this moving coil. Anyhow, this main magnetic field is constant. Okay, now here deflecting torque will be depending upon the current which is flowing through fixed coil as well as moving coil. So TD is directly proportional to the product of IF and IM. Okay, now let me write TD like this. TD is equal to IF IM dm by d theta. Okay, this is what, this is dm by d theta. What is M? M is mutual inductance between two coils. Here we are going to have two coils. Here we will not use any core. Okay, these two fixed coils are air cooled coils. Okay, In this also we will not use any core. Okay, this is also air core coil. Okay, so this also works on motoring principle. The only difference between these two is here we use permanent magnet, whereas here we use electromagnet. Okay, so now coming to the operation, let me pass alternating current through this fixed coil. Okay, now here see, for positive cycle of supply voltage, this will be the direction of current. Current will be flowing through the coil like this. Okay, if I use right hand thumb rule, then current will be flowing like this. Okay, then north pole will be induced here. Okay, south pole will be induced here. Similarly, south pole will be induced here, north pole will be induced here. Okay, for negative off cycle supply voltage, north pole will be induced here, south pole will be induced here. North pole, south pole. Okay, similarly, for positive cycle supply voltage, north pole, south pole, and for negative cycle supply voltage, south pole, north pole. Okay, so motoring action take place between these two coils. Okay, then this moving coil will be moving. As it is connected to this spindle, spindle also moves. If the spindle is moving, means pointer moves from zero deflection, as pointer is attached to the spindle. Okay, now coming to this mutual inductance. Okay, TD is given as IF IM dm by d theta. This is instantaneous torque. Instantaneous torque. Okay, now I'll do one first. What is mutual inductance? Okay, if I apply alternating voltage to this coil, then alternating current will be flowing to this coil. Then if I place voltmeter across this coil, okay, this flux links this coil so that EMF will be induced, right? Okay, now here mutual inductance will be, mutual inductance is equal to what? Mutual inductance is equal to voltage induced in the second coil by rate of change of current in the first coil, which is equal to, or voltage induced in the first coil by rate of change of current in the second coil, okay, which is equal to this is equal to flux linkage in one coil by current in the other coil, okay. If there is more flux linkage, then you are going to have more mutual inductance, okay. Now this mutual inductance is depending upon the position of these two coils, okay. Suppose if two coils are near to each other, then you are going to have high mutual inductance. If two coils are far away from each other, then you are going to have low mutual inductance, okay. This mutual inductance is not only depending upon the position of two coils, but also depends upon the angle between two coils, okay. So let me take two fixed coils like this, otherwise two fixed coils, moving coil. Let me place moving coil like this. Let me consider other arrangement, that is, okay, this is case 1, okay, this is case 2, okay. In case 1, this moving coil is perpendicular to both coils, okay. Very less flux linkage. Here you are going to have very less flux linkage, okay, because flux will be flowing like this, flux in the fixed coil will be like this, okay, flux in the moving coil will be like this, okay. So this flux will not link this coil, so very less flux linkage. Coming to this case, you are going to have flux lines like this, okay. Anyhow, this coil is in parallel with this coil, okay. So more flux linkage means more flux linkage means more mutual inductance. Here very less mutual inductance, okay. So here M is changing with respect to the change in the position of the moving coil, that is, M is changing with respect to the angle made by this moving coil, okay. This is changing proportionally with respect to this angle, so dm by d theta will be constant, this will be constant, okay. This changes proportionally, okay. This is proportional to this, okay. With the change in deflection, M will be changing, okay. So So dm by dt will be constant. Now let us go for electrodynamometer type wattmeter. Wattmeter. You're going to have two fixed coils, right? In this type of instrument, you're going to have two fixed coils. Okay. Two fixed coils are connected in series. You're going to have moving coil also, right? Okay. Okay, this is moving coil. Okay, this is attached to the spindle. This moving coil is connected to the spindle. This spindle is supported on jeweled bearings for free movement. Right. You're going to have springs. Springs will carry current. Okay, other end of moving coil will come out like this. It is connected to the spring, other spring. It is connected to the other spring. Okay. Now let me place load. Fixed coils are connected in series with the load. Fixed coils are connected in series with the load. So two fixed coils are connected in series with the load in order to carry the current which is flowing to the load. Okay, these two coils will carry the current flowing to the load. This is load. The current which is flowing to this is IL. Okay. These two are fixed coils. Okay, fixed coil FC. This is moving coil MC. This will be moving. Okay, these two cannot move. That's why these two are fixed coils. These two coils are also called as field coils. These two coils are also called as current coils. Current coils, as they carry current which is flowing to the load. Okay, and these two coils are connected in series with the load to carry the current which is flowing to the load. That's why these two coils are also called as current coils. Okay, now coming to the terminals of this instrument, M, this is M and this is L. L means load side. M stands for mains. Okay, M stands for mains. L stands for load. Okay, this is C sorry, this is V, this is C, this terminal is C, this terminal is V. Okay. If I want to use this instrument as that meter, what I do is I will join these two terminals, MC. I will join MC. MC terminal should be shorted. Okay, we are going to have MLCV. MLCV. M stands for mains, L stands for load, C stands for common, M stands for voltage. Okay, now this is connected to this. Okay, so if I want to use this instrument as wattmeter, MC should be shorted. MC terminals should be shorted. Okay, M is connected to the C. Okay, now this instrument can be used as wattmeter. Okay, this terminal is connected to this neutral wire. Okay, phase neutral. Okay, we apply single phase AC supply, right? Okay, if you want to use electrodynamometer type instrument as wattmeter, we short these two terminals. Okay, now okay, these two coils are connected in series with the load to carry the current which is flowing to the load. Okay, now this moving coil carries the current. Okay, the current which is flowing to this is what? IM. The current which is flowing to this is what? IF. Okay, IF, right? Okay, the current which is flowing to this, this moving coil carries current, that is IM, which carries current proportional to the applied voltage, because which is connected across the applied voltage, right? Okay, so this moving coil is connected across the applied voltage. This coil carries current proportional to the applied voltage. That's why this also called as, this moving coil is also called as voltage coil, VC, voltage coil, or pressure coil, because this coil carries current which is proportional to the applied voltage, because it is as it is directly connected across the voltage. Okay, which is connected across this voltage, applied voltage, right? This moving coil is connected across the applied voltage, right? So this coil carries current proportional to the applied voltage. That's why this is also called as, this moving coil is also called as voltage coil or pressure coil. Voltage coil or pressure coil. Okay, now anyhow we connect we connect a high non-inductive resistance in series with this moving coil. Okay, that is not shown here. Okay, anyhow we connect a high non-inductive resistance. A high non-inductive resistance is connected in series with this moving coil. To limit the current. Okay, to limit the current to a small value, we connect a high non-inductive resistance in series with this moving coil. Okay. Okay, these two are fixed coils. They carry current which is flowing through the load, right? Okay, and these two coils can be made more massive. These two coils can be made more massive to carry considerable amount of current. To carry considerable amount of current, these two can be made very massive. These two are having large cross section area to carry considerable amount of current. Okay, coming to moving coil, anyhow this is connected across the applied voltage and which carries current proportional to the applied voltage. Okay, here we use spring control method. Okay, with the deflection of the pointer, spring is twisted in opposite direction so that control torque can be provided. Okay, here we use air friction damping. Okay, here air friction damping. Okay, here we use air friction damping. Okay, aluminum piston is placed in this closed air chamber. One end of aluminum piston is placed in this closed air chamber, and the other end is connected to the spindle. Okay, when the pointer is trying to oscillate, okay, anyhow this carries pointer. You can also connect pointer like this. Okay, when the pointer is trying to oscillate, this spindle will be oscillating. When the spindle is oscillating, this aluminum piston also tries to oscillate in the presence of air, but this air doesn't allow this aluminum piston to move. Okay, when the air is not allowing this piston to move, means indirectly which is not allowing this pointer to move, to oscillate. So oscillations will get controlled with the help of air friction damping. Okay, coming to scale and pointers, here we use mirror type scales. Okay, normally we use mirror type scales and knife edge pointers, okay, to remove reading errors due to parallax. Okay, to avoid parallax errors, normally we use mirror type scales and knife edge pointers. Okay, now we'll move on to the expression for deflecting torque in this type of wattmeter. Okay, theory of electrodynamometer wattmeter. Instantaneous torque is given as Ti is equal to If Im dm by d theta, right? Okay, these two are instantaneous values. Okay, let me draw the circuit of wattmeter. Okay, anyhow you are going to have current coil which is in series with the load, which is connected in series with the load, right? This is what this current coil. Okay, this is applied voltage, phase, neutral, single phase is supplied, right? Next we have pressure coil. Okay, pressure coil which is connected across applied voltage. Okay, so this is pressure coil. We connect a non-inductive resistance, a high non-inductive resistance, in order to limit the current which is flowing through this pressure coil, because springs are used as current carrying conductors over here. Okay, so this is what this is pressure coil, this is what this is current coil. The current which is flowing through this is current coil IC. Okay, here in place of, see, Im is nothing but Ip, If is nothing but Ic. Okay, so the current which is flowing through this is Ip. Okay, simply you can write I F means C, right? IC Ip dm by d theta. Sorry. What is the instantaneous value of applied voltage? Normally you take small v is equal to Vm sin omega t, right? This is the applied voltage. If this is applied voltage, means this is nothing but root 2 V sine omega t, where V is RMS voltage. Okay, Vm is equal to root 2 into Vrms, right? Or Vrms is equal to Vm by root 2, right? Okay, so instantaneous voltage is equal to root 2 into V sine omega t. Okay, now we consider this is resistive in nature. We consider this pressure coil is resistive in nature. Okay, if the pressure coil circuit has a very high resistance, okay, that is, it can be treated as resistive circuit. This pressure coil circuit can be treated as resistive circuit. Okay, then only we can measure true power. If this pressure coil is resistive in nature, then only we can measure true power. Okay, so it is better to make this pressure coil as resistive as possible. Okay, then if it is treated as resistive circuit, if this pressure coil is treated as resistive circuit, then what will be the current flow into that? IP is equal to that V by, let Rp is the resistance of the pressure coil. You are treating this as resistive circuit. Okay, resistive element. Okay, so then you are going to get root 2 V sine omega t by Rp. Then you are going to get root 2 IP. Okay, this is RMS value now. Root 2 IP sine omega t. Both are in phase. Okay, applied voltage and this current will be in phase, because you are treating this as resistive element. Okay, now what about the current flowing through this current coil? This is what? This is load. Anyhow, normally we use lagging loads. If we use lagging load, IC will be equal to root 2 IC. IC is nothing but the current which is flowing to the load. Okay, you take simply, it is I, root 2 I sine omega t minus phi, because we use lagging load. If I use lagging load, current lags voltage by an angle phi. Okay, then instantaneous torque will be IC IP dm by d theta is equal to root 2 I sine of omega t minus phi root 2 IP sine omega t dm by d theta. Then Ti is equal to 2 IPI sine omega t sine of omega t minus phi dm by d theta, then which is equal to 2 sine A sine B. Then you are going to get IPI cos of A minus B minus cos of A plus B. So cos phi minus cos of 2 omega t minus phi dm by d theta. We are not interested in instantaneous torque, because instrument only takes average deflecting torque. Okay, it responds to average deflecting torque. Okay, due to inertia, instrument responds to average deflecting torque. So let us find average deflecting torque. Average deflecting torque. That is TD is equal to 1 by T integration 0 to T Ti d of omega t. Okay, which is equal to 1 by T integration from 0 to T IPI cos phi minus cos of 2 omega t minus phi dm by dt. Then you are going to get, okay, after solving this you are going to get IPI cos phi dm by d. Okay, after applying integration on this, integration of this, and after substituting limits, okay, this will become 0. Okay, then you are going to get IPI cos phi dm by d. So TD is equal to IPI cos phi dm by d, which is equal to this IP. IP is the current which is flowing through the pressure coil, right? Okay, nothing but applied voltage by resistance of that pressure coil. V by RP is nothing but IP, right? Into I cos phi dm by d is TD. Okay. From this equation, TD is directly proportional to VI cos phi. That is, TD is directly proportional to AC power. TD is directly proportional to AC power. Okay, so this instrument can be used as wattmeter. Okay, this instrument can be used for the measurement of power like this. Okay, as TD is directly proportional to VI cos phi. Okay, deflection is directly proportional to VI cos phi, AC power. Okay, now let us find deflection, steady state deflection. Okay, so anyhow we use spring control method. As we use spring control, TC is equal to Kc theta. Okay, at equilibrium or under steady state condition, TC is equal to TD, then Kc theta is equal to V by RP I cos phi dm by d theta. Then theta is equal to V by Kc RP I cos phi dm by d theta. So from this, theta is directly proportional to AC power, VA cos phi or AC power. Okay, thank you.